Hi physics, welcome back. This is from homework 5. This is problem 3. We've got Denise. Her mass is 60 kilograms. She's skiing down a hill, and the hill's got a 35-degree incline. The coefficient of kinetic friction between her skis and the snow is 0.150. So we want to know what is the normal force on the sled, and also how fast will she accelerate downhill. So as usual, first thing we do is step Part A. What are we looking for? We want the normal force, so F sub n is equal to question mark, and we expect it to be in newtons. And B, how fast will she accelerate downhill? A sub x, trust me for now, it is A sub x, is equal to question mark meters per second squared. It might not seem like that's A sub x, but it actually is. So this problem is really neat. I like this problem. It's a little tricky at the beginning, and then after you get through that trick, it ends up being just like all of the other force problems we do. So first thing we have to do is make a sketch of what's going on. So I'm going to make this big because this is going to be tricky. And it's important we have a clear idea what's going on. So first things first, it's a 35-degree incline. So this problem, it's very important that you get your angle correct. Theta is equal to 35.0 degrees. Sorry, a little hard to write this. Denise is skiing. So here's Denise. Is it Denise? It is Denise. So she's skiing. She's going like this. She's got speed line. She is skiing downhill. And we know a bunch of other things. I'm going to leave those out because this drawing is going to get crowded enough as is. So I'm going to draw in my vectors here. I'm kind of mixing step 2 with step 1, and then I'll do step 2 separately, but you'll see why. So first things first, what forces are going on? Well, if you think about it, if you're skiing, what makes you go downhill? That's gravity. Separate question, what keeps you stuck to the hill? That's also gravity. So that's a little bit weird. How does that work? So the way that works is the force of gravity is actually going straight down towards the center of the Earth. So that is down. What other forces do we have going on? Well, her skis are touching the hill, so there must be a normal force, which means perpendicular. The thing that's a little bit weird is it's perpendicular to the hill, so it's not straight up in the air. It's actually perpendicular out of the hill. So I'm going to draw it in like that. So that's a little weird. The other thing that's going on is there's friction. There's friction between skis and snow. She's going down the hill, so which way is the friction going? The friction is going straight back up the hill like this. So F sub k is going like that. We don't have any other forces. There's not a force of Denise going down the hill. There is her weight, F sub g, going straight down towards the center of the Earth. But what you don't want to do, so this is bad, is don't draw an arrow like this. There's not another force for that. So I'm getting rid of that. So if we look at this, what vectors are pretty and what vectors are ugly? At first glance, it seems like F sub g is your only pretty vector and the other two are ugly. But that's actually not the way you want to do this problem. So your entire life, when you've done math, y was up and x was to the right. Seems very normal. However, we're actually not going to do it that way. Our life is going to be simpler if we make y out of the hill. So this is the new y, and x down the hill, which looks a little crazy if you're not used to this. The key thing is that's still a right angle, just like it was before. And as long as x and y are perpendicular to each other, the math is going to be happy. So how does this help us? Why is this any better? We've gone from having one pretty vector and two ugly vectors to now having two pretty vectors and one ugly vector. So that's good. So again, I'm combining step 2 with step 1, and then I'll do step 2 correctly a little bit separately. What's happening here? This is weird. What you want to do, and this is why it's so important to draw your triangle correctly, is think about what portion of Denise's weight, F sub g is her weight going down, what portion of that is going into the hill, so what portion of that is going this way, and what portion of that is going down the hill, going this way. And if you draw your triangle correctly, you might be able to see that this is in fact a right angle, and this is actually theta. This is the same 35.0 degrees. Theta equals 35.0 degrees. If you haven't drawn your triangle correctly, it's going to be really confusing. Well, is that one theta or is this one theta? No, I had it right the first time. That guy up there, that is 35.0 degrees. So what that means is the portion of this that's going into the hill, I'm going to call that F sub g y, because that's in my new y direction, into the hill. And the portion that's going down the hill, like along the hill, that is F sub g x, like this. So again, if you're not used to seeing this, that might look a little bit weird. Trust me, that's the right way to do it. So once we do this, let's do our step 2. And we'll end up doing this twice, actually, just to be really thorough. So step 2 is free body diagram. There's different ways to do this. Since we're doing something sliding down the hill, I think the actual best way to do this is draw your free body diagram on a tilt. Just remember that from now on, that is our new y direction. This is our new x direction. So what forces do we have here? We had the normal force going like this, which remember, that's our new y direction. So that is a pretty vector. We had the force of friction going like this. So F sub k is going back along the hill. So that's still a pretty vector. Sorry, F sub k. And we had one ugly vector, which was just gravity going straight down. So this was the old negative y direction. In our new coordinate system, this is the ugly vector. So we have to do a step 0 to this guy. Sorry, I'm trying to move the thing out of the way. Okay. So we have to do a step 0 to that guy. Let me quickly redraw that. So here's the ugly one. So that was our box. That was our normal force. This was our force of kinetic friction. And the force of gravity was going down like this. So in our new system, force of gravity is the ugly vector. So what we want to do is a step 0 to that guy. So again, remembering that this is the new y and this is the new x. If we have this vector like this, how do we get the components? The new y direction is the one that's going like this. The new x direction is the one that's going like this. This is a right angle. This is F sub g. This is theta. And this is F sub g y. And this is F sub g x. So very important you draw your triangle correctly. Let's go back and look at the other one. Convince yourself that this business here is the same thing I've just drawn over here. So what is F sub g equal to? Well, that's equal to mg. I can get that number right now if I want. That might make my life a little bit easier. So mg is equal to 60.0 kilograms times 9.8 meters per second squared. And F sub g is equal to 588 newtons. All right, now let's do our trig carefully over here. So if we're looking at this triangle we've got here, F sub g, this side is the longest side. It's opposite the right angle, so that's the hypotenuse. Which side is adjacent? Which side is opposite? F sub gy, this side here, this one is the adjacent. F sub gx, this is the side that's opposite. So that might look a little different than how we've been doing it, but trust me, that's the right way to do it. So now we'll go and we'll figure out what these numbers are. So F sub gy is going to be equal to F sub g, the adjacent side, so that must be cosine of theta. Plug in the numbers, so F sub g, 588 newtons, times cosine of our angle was 35 degrees, and we end up with F sub gy is equal to 481.7 newtons. Circle that because that's important. F sub gx, well, this is equal to, now I'm getting a little bit crooked, F sub g, this is the opposite side, so this must be the one that's sine theta. So plug in 588 newtons times sine of 35, and you're going to get F sub gx is equal to 337.3 newtons. And I'm going to circle that, and then I'm going to do my small, medium, large test. So this side, this is the small side, and that gets the small number. This is the medium side. That gets the medium number. And this side here, the hypotenuse, that is always the large side. So that gets the large number. So this passes the small, medium, large test, which is really important to do because in something like this, it gets really confusing very quickly. This probably means I did my trig correctly. So I'm happy with that. Now I'm going to do a new step 2. I'm going to switch to black just to make it a little easier to see. And just like before, step 2, but only with the pretty vectors. So remember, just again, that's our new y direction, this is our new x direction. As long as they're perpendicular, as long as that's the right angle, math is happy. So we're going to redraw our box. What forces do we have? We still have the normal force going this way, that was always a pretty vector. We still have the force of kinetic friction going this way, that was always pretty. But now instead of drawing this ugly vector, I'm going to replace it with its two pretty components. So I have F sub gy going in my new down direction, so F sub gy, and I have F sub gx going in my new x direction. This is downhill. So yeah, that's the key to doing this problem. So I'll do another video to actually finish this. But if you've gotten this far, from here on out, it's honestly just a regular two-dimensional force problem. Do the y side first, and then do the x side. So let me stop this one here, then I'll do another video, and I'll finish it in that video.